Hey Justin,
Yes, Brandon.
I wonder what happens when two objects exert force on each other.
Good question. Don't worry. In our next video, we'll have Ryan Tan and Josh Alfonso demonstrate that for you.
Great, thank you.
Dude, what happened?
I don't know.
We just like bounced off each other.
You're really bouncy.
Yeah, like what phenomenon could have caused that?
In the video we just saw, both Ryan and Josh were not paying attention and eventually bumped into each other, creating a force. Force, as defined by Sir Isaac Newton's second law of motion, is force is equal to mass times acceleration. This means that the bigger and faster the object is during motion, the greater the force it has. The following video will explain why Ryan and Josh bounced off each other and why they both felt bouncy.
Whether it's a lineman stuffing a running back or a safety colliding with a wide receiver, all NFL defenders have a single-minded goal: to stop the ball carrier.
The object of making a tackle is you want to get the guy down and limit the amount of yards he's able to gain, especially after contact.
When a tackle is performed correctly, it's not just a thing of defensive beauty. It's also an elegant depiction of Newton's third law of motion, sometimes called the action-reaction
Newton's third
law.
law says that each action or force has an equal and opposite reaction. So if I were to push against a body, that body is going to push back against me with an equal and opposite force.
An important part of Newton's third law is the concept of momentum, which in football is the mass of a player multiplied by his velocity, represented by the formula P equals mv. NFL players may not know the formula, but they're keenly aware of the role momentum plays in tackling.
It's very important to have some speed and momentum as you're going in to make that tackle. The better you're able to use that to your advantage, the better you're able to make contact and get a guy down right away.
In every collision on the football field, Newton's third law dictates that the total momentum between players must be the same before the collision as it is after the collision. This relationship is referred to as conservation of momentum.
The law of conservation momentum says that the P, the momentum before the collision, is equal to P, the momentum after the collision.
This law, represented by the formula P before equals P after, can be illustrated with a simple toy called a Newton's cradle.
In this case, we have displaced an initial sphere, and when we let it go, it has some momentum. It's mass times velocity. When it impacts the next sphere, that momentum is transferred through the middle three spheres and then passed on to the final sphere. And so because it has the same mass, it will move away with the same velocity that the first sphere impacted the middle three spheres.
The interaction of balls on a Newton's cradle can help illustrate what's known as an elastic collision, defined as one in which there is no loss of kinetic energy in the form of heat, sound waves, or deformation of the object. On the football field, collisions are typically inelastic collisions because kinetic energy is released, mostly in the form of compression between the players' bodies and sound waves.
Inelastic collisions are the rule of the day. We see them all the time in football. That is the energy of motion of two runners. After they collide, that energy is dissipated in deforming their bodies. That's like a spring. So some of your energy of motion went into that compression. You might have heard a loud snap from our pad. Some of the energy of our collision was transferred to the energy in the air that you hear.
While big hits look and sound spectacular, what's most important in tackling is stopping the ball carrier's forward progress.
If your pads are underneath his and you're hitting on an upward slope, you direct the energy up and you take him back. At the point of contact, hopefully that's where the ball stops play in.
Whether a tackle is successful or not, we can be certain that the same force is exerted on both players, and the total momentum before and after the collision is the same. For that, we have Newton's third law to thank.
I don't get it. Can you give like another example or something?
Hey Ryan, I'm glad you asked that question. Don't worry, our best friend Oprah will help us solve that. And I'm sorry, you don't get a free card today.
Newton's cradle, it actually was not invented by Newton. It's named after Newton because it demonstrates, yes. I know. So it's your classic desk
This is
toy,
a great
but
one.
way bigger. So the ball will come down. Now it's going to pull this first ball back. When it's released, it's going to start moving in this direction. Now, if you notice, these things are just hanging out.
Yeah.
They're just being lazy, so they don't want to go anywhere till another force acts on them. Now, when it collides, it's going to exert a force on that first ball in the chain here. It's going to transfer all of its energy to that one, and then it's going to stop because that ball pushes back on it. See? So you have an action-reaction pair that happens. It sends all that energy all the way down the line until you get to this last one.
Newton didn't create this. Who created it? It's named after Newton, who was the originator. He didn't have the balls.
I don't think I can top that. So instead, if you can't beat them, change the topic. Should we go this way? So, my friend Brett is another scientist here at the museum. So what he has is a beaker full of liquid nitrogen. So what we're going to do, now we're going to turn the bottle into a rocket. So he's going to fill the bottle with liquid nitrogen.
Yeah.
And then we're going to cap it off with this cork. So what's going to happen, liquid nitrogen is a super, super cold liquid. So right now, this room is just boiling hot to it. So it's going to start turning into a gas very rapidly. Pressure's going to start building up in there, and that's going to exert a force on the bottle and the cork. When that force gets big enough, it's going to shoot the cork off in one direction and the bottle off in another, in an equal and opposite reaction. All right, you ready? It's going to happen very quickly once he caps this off. So the cork is going to go into the top of the bottle. It's going to exert a force. As that force builds up, it pushes on the cork in the bottle. Eventually, they shoot off in opposite directions.
Equal and opposite.
To wrap it all up, we learned 2 key points today. So the first is that force is equal to mass times acceleration, and this defines how strong or weak a force is.
The second is that Sir Isaac Newton's third law of motion states that for every action, there is an equal and opposite reaction. And this explains why both Ryan and Josh bounce off each other in equal and opposite direction.
Oh, I get it now. Thanks, Oprah.
Thank you for watching our video. We hope you learned a lot about physics today. Until next time.
I'm Justin.
I'm Vania.
No, you lied.
What?